I will be demonstrating Gay-Lussac's law. Gay-Lussac's law states that temperature and pressure are directly proportional so long as volume and mass remain constant. It can be represented in the formula below. This means as temperature increases, pressure increases, and vice versa.
Here, I cover 2 lit candles with a glass surrounded by water. As the candles extinguish, the water level inside the glass rises. As the candles burn, the main gases surrounding are O2, CO2, and water vapor. The thermal energy from the flame puts the molecules in an excited state. When trapped, the excited molecules move faster and hit against the walls of the glass and create a high pressure. The flame extinguishes and takes away the thermal energy, and the molecules reduce collisions. Since the pressure in the system is lower than the surroundings, it compensates by the higher water level.
Charles' law states that the volume and temperature of an ideal gas are proportional so long as the mass and the pressure remain constant. This can be represented in the formula below. This means if temperature increases, volume increases, and if temperature decreases, volume decreases, and vice versa. To demonstrate Charles' law, I'm going to be using a balloon, boiling water, and ice water. So right now, the width of the balloon is about 5.5 inches. And now, as I put it out in the boiling water, it should expand. As you can see, it is expanding a lot. And I will quickly measure. It is about 6.5 to 7 inches. My trusty string here. And that was at the peak. So now I will submerge it in cold water. Rotate it. It's really cold. So. I need the ruler. Now, it measures at around 4.75.
When the balloon is introduced to an atmosphere with high thermal energy, the molecules inside the balloon spread out and move faster, push up against the walls of the balloon, and increase the volume. When the balloon is introduced to an area of low thermal energy, the molecules slow down and move closer together. This decreases the volume of the balloon.
Boyle's law states that the pressure and volume of an ideal gas are inversely proportional so long as the mass and temperature remain constant. This can be represented in the formula below. This means that if pressure increases, then the volume decreases, or if pressure decreases, then the volume increases. I will be demonstrating this law with marshmallows and a syringe. Right now, you can see that the marshmallows are around the 5.5 mark. I will cover my thumb over the opening of the syringe so that the air inside will stay the same amount. As you can see, as I pulled the stopper, the marshmallows expanded. There you go. This time, to show the reverse effects, I will be using 2 new marshmallows and instead using the plunger to start up here. I'll cover my thumb over the opening, and as the plunger goes down, you can see that the marshmallows get smaller. And if I remove my thumb from the opening of the syringe, then the marshmallows will return back to normal size.
To start, the pressure inside the syringe is equal to the pressure of the surroundings. As the plunger moves outward, the pressure decreases and the molecules spread apart. This increases the volume as demonstrated by the marshmallow as it tries to compensate for the unoccupied space. Reversely, when the plunger starts out and moves inward, the pressure inside increases and the molecules are pushed closer together and push against the marshmallow. This decreases the volume.
First, I will be demonstrating Gay-Lussac's law. Gay-Lussac's law states measure the diameter now. It is about 6. 6.5. As temperature increases, pressure increases.
Me to breathe. Tell me how I'm supposed to breathe with no air.